So you know that spooky action at a distance that famously freaked out Einstein? Well, what if I told you it's not just for the quantum world anymore? We're about to dive into a wild new paper that shows how to actually engineer a version of entanglement in the classical world we live in every day. Yeah, it sounds pretty much impossible, but trust me, the results are going to bend your brain a little.
Right. So let's just quickly touch on quantum entanglement. It's this bizarre, almost magical connection where two tiny particles can be linked, and when you measure one, you instantly affect the other, even if they're light years apart. It's one of the weirdest, most profound ideas in all of physics.
But that leads to the really big question here. Can a version of that spooky link exist for things that aren't quantum? I mean, could we actually build and control entanglement-like connections in the normal classical world of, say, tiny jiggling particles?
To figure that out, the scientists came up with this beautifully simple model. Seriously, it's just two particles, an invisible little spring that connects them, and a whole lot of chaos. Let's break down how they set this whole thing up.
Okay, first you gotta picture the environment these particles live in. It's all about Brownian motion. Just think of specks of dust floating in a sunbeam, constantly getting knocked around by air molecules. That's their world, a totally random, chaotic, jiggling dance.
So the brilliant idea was to take two of these little jiggling particles and link them together with what's basically an invisible spring. And then, and this is the real secret sauce, they decided to actively poke one of them to drive it and see if they could get their connection to act like entanglement.
And here's exactly how they did it. First, they put each particle in its own little energy trap to hold it in place. Then, they hook them up with that spring. Next comes the fun part. They start messing with particle one's trap, making it tighter or looser over time. This is what scientists call non-equilibrium driving. And finally, they just sit back and measure how connected the two particles become.
So how do you even measure something like entanglement in a system like this? It's not like you can just look at it and see it happening, right? You need a special kind of detector, a mathematical tool that can tell you if something truly special is going on between them.
And that detector has a pretty cool name, an entanglement witness. Don't worry about terms like osmotic velocities. Just think of this thing W as a number. Its whole job is to watch the particles and scream, "Hey, something special is happening," when their connection becomes non-separable. That's just a fancy way of saying you can't describe one particle anymore without also describing the other.
So it all boils down to this one simple rule. You take the temperature of the system, call it T. If their measurement, W, ever drops below 4 times that temperature, below 4T, they've done it. They've created what's called Brownian entanglement. That's the whole game. Can they push that number below the magic line?
All right, now for the results. The first big question they asked was, does it actually matter how you drive that first particle? You know, is a slow, steady push any different from a quick, sudden jolt? So they tested a few different methods, or protocols, for messing with that trap.
And the answer was a huge yes. It totally matters. Take a look at this graph. See that red dashed line? That's our goal line, 4T. Anything that dips below it is a win. Now, when they run the experiment really fast, you can see all 4 methods work. But check out the bottom right, where the process is much slower. That smooth, gentle curve stays entangled for way longer than the others. So yeah, how you do it is critical.
And that right there is a huge takeaway. It's not just that you're pumping energy into the system, it's how you do it. The exact shape and timing of your poke acts like a precision control knob, letting you engineer not just if, but for how long these special connections exist. It's a whole new level of control.
Okay, so the driving method is one control knob. But what about the spring itself, the connection between the particles? You'd probably think that a stronger spring would mean better entanglement, right? Well, you might be surprised. Check this out. This graph shows what happens when they play with the spring's strength, which they call G. If the connection's too weak, yeah, it gets entangled, but it fizzles out really fast. If it's too strong, same thing. The dip is super brief. But look, right there in the middle, around G equals 0.5, that's the sweet spot. That's where the entanglement lasts the longest. It's like if the spring is too weak, the signal gets lost, but if it's too strong, they just move like one rigid object, and you lose the subtle correlation.
And the researchers say it themselves, it's not about making the connection as strong as possible. No, it's about finding the balance. There is a perfect, just right strength that lets this spooky correlation hang around for as long as possible. Okay, so this is all incredibly clever, but let's zoom out. What's the bigger picture? I mean, why does engineering spooky connections between a couple of jiggling particles actually matter?
Let's just run through the main takeaways.
1. Entanglement isn't just for quantum mechanics anymore. We can actually build it. 2. How you add energy is a super important control knob. 3. The connection has a Goldilocks zone. It has to be just right. And all that adds up to a completely new way to control the microscopic world.
And that really is the heart of it. This isn't just a cool party trick for physicists. It's about gaining a much deeper understanding of how information and connections work in these mesoscopic systems. That crucial borderland between the tiny quantum world and our big classical world. This is about learning the fundamental rules of control.
And that kind of leaves us with one final mind-bending thought. If something as bizarre as entanglement has a classical version we can actually build and control, what other quantum mysteries might have a cousin hiding out in our everyday world, just waiting for the right experiment to come along and find it?